payload, is currently the payload module manager for the JPL Earth Science mission called SWOT, Surface, Water, Ocean Topography Mission. She has been at JPL for 25 years, worked on advanced concepts and flight projects, and has held several line management positions, including she was the recent division manager in the mechanical systems divisions at JPL. She is also currently a NIAC fellow, completing her phase 2 NIAC phase task on printable spacecraft, flexible electronic platforms for NASA missions. And this is the topic of your presentation. So.
Okay, great, thank you.
So please welcome Kendra.
Hi. Hi, good morning. My talk today is going to be a little bit broad-based. I'm going to talk about a couple of technologies, hopefully that will get people thinking about possible implementations for the concept that we're going to be working on this week. And it includes an overview of two-dimensional and three-dimensional printing, and also a description of my task, which is the printable spacecraft, which is currently 2D electronics printing. So the topics that I'm covering, I think almost everybody in the audience is aware of this, but these are the two main topics that I'll be talking about. I think everybody has heard of MakerBots and 3D printing of structures and things like that. But maybe not everybody has heard about two-dimensional printing of electronic circuits and devices. And so I'm going to talk a little bit about those two items and how those two can be combined together from some very interesting implementation concepts. So as an overview of 3D structures printing, essentially 3D printing is an additive process, not subtractive, which is the traditional approach to manufacturing of parts and structures. Really, 3D printing applies mostly to generating a structure, a shell, a truss, an object of sorts, through slices, maybe 100 micron thick slices, and stacking those all up, fusing those layers together, and you get your 3D structure out of it. It really starts with a digital CAD file, which is sometimes prepared for manufacturing if you have certain features about your structure that needs to be modified to support it during that process, overhanging lips and things of that nature. Sometimes there's a little manipulation of the CAD file to make sure it's compatible with the manufacturing, but not too much. The types of 3D printing include the very first concept that came out is stereolithography. It's a vat of liquid resin, and a UV laser comes in and fuses or hardens the resin in the particular areas, and you pull out of the vat at the end your hardened structural part. We've seen lots of those around. Here's an example of that. Newer technology is the fused deposition material, or FDM. This is what is the concept behind the MakerBot and things like that. The term fused deposition material is actually a patented term, so the more generic term is fused filament fabrication. And basically you feed a plastic, a thermoplastic or something off of a feedstock into the head. You melt it and fuse it to the adjoining structure, and you just add material as opposed to creating something out of a vat. You just add material where you want it to be. And you can do all kinds of intricate internal structures and things like that because of the various layering. Something more interesting is selective laser sintering. Because NASA doesn't fly a lot of plastic parts. This is similar to the stereolithography, but the vat is a powdered can be a different powdered material, either a polystyrene or a ceramic, even metallic powders and things like that. But the process is about the same, where you inject a laser into the vat, and the material hardens or fuses where you want it to, and you pull out of your vat your final part. The really interesting new technology is called laser engineered net shaping, which is basically, there's a picture of it right here. You're injecting a metal powder into a melt pool that's created locally on the part that you're fabricating with a laser. a high-powered laser. It's also called direct metal deposition. And the thing that's interesting about this is because you're not dealing with a vat of material, you can do large structures. You're not constrained by the size of the structure that you can do. You can also tailor materials, which is actually an area of research that JPL is doing in Division 35, where you can mix different materials and tailor the properties as you see fit through your part, so you can get varying CTEs or varying compositions from titanium to aluminum or combinations there in between. And the key company there, I've listed some of the key companies, is Optomech. They have a very interesting machine that will do that. The other improvement over some of the other rougher parts is you can get near net shape, so you have very little final machining of your part when you're done. There's a bunch of other methods, but these are really the main areas of 3D additive structural manufacturing. There's a lot of commercial applications that you can't do a YouTube search without finding something interesting about 3D printing. Mostly in model making and prototyping. There are some automotive parts that are made with 3D printing, some aerospace parts, and a lot of novelty parts, little toys and gizmos and gadgets. 3D printed sugar and chocolate, which is my personal favorite. And fashion, 3D printed shoes. I'm not sure who would wear those, so that's kind of 3D structures printing in a nutshell. What the area that I'm working in is 2D flexible electronics printing. The basics are that this technology uses a substrate. It could be flexible, like a Kapton sheet or a other sort of polyamide sheet, and it could be stretchable. There are stretchable substrates, and there are dissolvable substrates, especially for biomedical applications and things like that. You combine that with an ink, and these are called functional inks, either a conductor or an engineered polymer, even a photoreactive kind of ink, and you apply those with a variety of manufacturing approaches, depending on whether you want a small size, like a sheet-based production with high precision, or you want a roll-to-roll, high volume, high production type of application. And you can do a variety of different types of manufacturings, from inkjet, literally a PZT deposited inkjet type of system, to maybe a gravure type of ink on a master roll and a master cylinder, or even something more exciting like an E-jet system, which generates an electric field and draws the fluid down onto the surface. And this is about the most precise that you can get right now. So with those various types of applications, you can generate basic devices and circuit elements similar to the construction techniques that you just saw in the previous presentation, but these are applied with the printer as opposed to having discrete devices being assembled. And so you just simply layer on and print on the various layers that you need for the functional device. This is a transistor that's got 3 or 4 different layers. This is a battery construction. This would be the construction of a solar cell. And you just choose the material that you want, layer it up, and these can be 75 microns or so, very, very thin devices. When you combine some of these basic building blocks, you can get electronic circuit elements. These were all produced by Xerox PARC, and then you can obviously combine those together to get the functional circuit and the functionality that you need out of your system. So where's the printed electronics industry going? We talked about model making and shoes and sugar for 3D structures, but where's the printed electronics industry focused? It is a very large industry, primarily focused on interactive screens and large flexible displays, and also RFID tags and smart packaging. That's really where the money's at for printed electronics. There are some more interesting systems for military applications, smart sensors that they can fly on aircraft platforms, or intelligent military uniforms. There's also some very interesting work being done by John Rogers for biomedical, for embedded sensors that can perhaps map the seizure patterns and locations for epileptic seizures in the brain by having an integrated circuit conformal right to the brain itself. There's also a lot of work in photovoltaics, although it hasn't really materialized into a very profitable business. But you can make these so thin that they're transparent. You can color them however you want, and you can integrate your solar cells into the windows of your building and produce a power grid for your building without having panels, or you could embed them in the panels of your car. So a lot of different areas where printed electronics is going. These are some of the headlines that we've probably seen on the revolutionary, disruptive, game-changing sort of things that are happening with 3D printing and printed electronics. But really, what is relevant to NASA? We don't make shoes or sugar. So what is really interesting to NASA? The 4 characteristics that I highlight in this technology that's of key interest to NASA is primarily it's enabling new products or benefits to old products. The new products are structures that you couldn't design and manufacture and assemble in a cost-effective way any other way than with 3D printing. For example, the embedded gears or rotational systems that you don't have to assemble together. You can build your rotational structure inside the other structure. So completely new systems that you can bring new designs to bear that are really not effective any other way. The other interesting thing is it makes use of a universal raw material. Rather than having to stock sheets of 7075 of this thickness, of this forging size, whatever that takes 6 months to order. Yeah, I've got 2 tons of aluminum 7075 powder. I'll make your part next week. Thanks very much. So very interesting things, common starting point for many things. Highly efficient use of materials. It's additive, not subtractive, so there's no waste. There's no byproducts, no recycling. Things of that nature. It's also digital, which makes it reconfigurable, editable, and uploadable when we talk about autonomous stations. So if you're printing your products on Earth and launching them up into space, features 1 through 4 certainly allow you to optimize your systems for the things that we really care about: strength, weight, volume, cost, schedule. But if you're manufacturing in space, which is another concept that's very interesting, features 2 through 4 really make this enabling. You can imagine a manufacturing plant on the ISS, on the moon, a robotic plant on Mars, where you really want to start with a common raw material and make anything you want out of it, use as little material as possible, and upload your file to execute as you see fit. So the other thing that's interesting is when you start talking about multifunctional hybrid systems where you combine traditional electronics with printed electronics, or printed electronics with a traditional structure, or even printed electronics with printed structures. Things really start getting interesting at that point. And this is a picture of the ISS MakerBot that's flying this year. This is another NIAC fellow, contour crafting, where you're generating concrete structures on the moon with in situ material and things of that nature. So it can get very interesting. But really, what is a printable spacecraft, which is the NIAC task that I'm working on? Our concept was really to edit the spacecraft to the full spacecraft design digitally on the computer, and then be able to send it to a printer and deploy thousands of copies of these. Just hit print, quantity 1000, and you're done. So really a printable spacecraft is a 2-dimensional sheet, one of these thin, flexible substrates that contains all of the functional systems that you would think of in a typical spacecraft. Everything from the science sensor all the way through the systems to get the data off and down onto the ground. Functional circuits would be designed compatible with flexible electronics and printing techniques, and all of the elements would be printed onto a common substrate. So that was the concept. We did some study in our NIAC phase 1 to see, can you really get all of the components? And yes, in fact, you can. If you look at all of the functions of a spacecraft, sensors, power generation, power storage, RF circuits and antennas, and even memory and logic, it's all available now in terrestrial applications in a printed form factor. So it's just a matter of putting it all together, right? So you might ask, why would you want to build a spacecraft out of this? Which the benefits of a flexible printed electronics, people have studied this for many years, mostly in sort of focused applications where there's really a key benefit, like deployable large area radar, where you need thin and flexible and deployable. But really the flexibility allows you these options for storage and deployment. It also is a lot lower cost when you get down into a reasonable manufacturing environment. So you can look at large numbers of individual platforms. The swarm concept, I think somebody talked about that. Or high-risk disposable environments where you don't really expect it to survive. Also, it's very low mass and low volume, so it doesn't take up much space on your host spacecraft, and you can use it as a secondary payload, and also short cycle times. Of course, there's significant challenges, which was the basis of our NIAC Phase 2. The component functionality isn't quite what you would get with traditional electronic systems. The complex science and sensors, you're not going to make a hyperspectral imager out of printed electronics. So what science can you do with a more simplistic sensor suite? Certainly the environmental compatibility, and we tackled sort of the integrated system design. So our Phase 2 task consists of 4 main elements. One, we developed a full end-to-end benchtop prototype that's been completed, and I'll show you some results. We also designed a reference mission to look at really the application of this and to see whether it's feasible and whether it makes sense. We're in the process of generating our test samples for doing some environmental compatibility testing, informed by our reference mission, which is a Mars surface mission. And we'll be doing that testing next month with Boeing. And then, of course, roadmaps and infusion paths and things like that. So I want to talk to you a little bit, I've got about 5 minutes left here, about our prototype demonstration. What we were trying to do was develop a highly functional, lightweight, mechanical, flexible prototype that has 2 different sensors and wirelessly transmits the data. So we have sensors, we have multiplexing circuits, we have 2 discrete chip elements, and we have the RF system. And so what we were trying to do, or to address sort of advances in the state of the art, it's really the intersystem functional compatibility of these various discrete elements. We included some low voltage TFTs, which were demonstrated for the first time. We demonstrated multiplexing of the sensors and actually developed 2 new sensor designs. So this is the overall system design. You can see we have 2 discrete chips. We're in the middle of proposing for a second generation that takes those discrete chips and converts them to the silicon on polymer systems that are flexible but more traditional silicon systems. You can see the components that we had here. And an overview, the whole system operates at 3.5 volts, which makes it very nice for the printed systems and the micro electronics to be compatible on the same power grid that you provide to the platform. So this is a picture of our sensors. We developed a thermistor in collaboration with a South African company, PST. And Park, Xerox Park, who is our fabrication partner and design partner on the NIAC, generated a photo sensor, a light sensor. And you can see the functionality has been demonstrated as individual sensors. We've also developed low voltage thin film transistors, which allow us, these are the characteristic curves, they allow us to turn on and off the input from those various sensors so that the data system can say, I want to record this measurement from this sensor now, I want to record the measurement from this other sensor now, and cycle through the sensors rather than getting a hodgepodge mash of continuous data. So this shows the functionality with the gate on and the gate off for the various sensors, and you can see that that circuit is actually working. The rest of the engineering systems, it's fabricated on a common PEN substrate. We've got our printed antenna directly on. The discrete components are attached with a flexible conductive adhesive, and you can see the difference in the resistivity in the lateral and vertical direction. So it allows you to basically print a glob of your adhesive and then attach your microelectronics after the fact, and it's compatible with the flexibility. So you don't really, for the size of these little electronic components, you don't lose the overall platform functionality. This is what the final unit looks like, and it's been email or mailed to me at JPL. I don't have it set up and working yet, but the data has been recorded at Park, and you can see the functionality of the 2 different sensors independently working on the integrated platform. And it wirelessly transmits that over the antenna to a near-field receive station. So what are the NASA applications for printed electronics? I've listed some of these here. I am running out of time. I see the yellow light glowing at me. And so, so I will skip this, but I do want to point out similar concepts to the intelligent structures that you saw in the last presentation. Printed electronics can also help in that regime as well. But I want to sort of end on a chart that really intrigues me, which is when you combine the 2D printed electronics and the 3D printed structure together on the same manufactured device. It really opens up the possibilities of some very innovative multifunctional systems. The MesoScribe Direct Write can print your circuits on any existing 3D structure that you have made either in a traditional fashion or with 3D printing. You can have embedded electronics inside the volume of your structure for your sensors. You can have robotic structures that are made with a 3D printer with embedded circuitry for force sensing, temperature sensing, and things of that nature. You've probably seen the Princeton ear. That's a 3D printed structure and embedded electronics. And Stratasys and Optomec have done 3D printing of circuits and sensors on a UAV platform, so that there's the electronics are integrated completely with the wing and the aircraft body. So very exciting possibilities when you start looking at combining this together. So really, additive manufacturing, I think, is exploding in the commercial arena, and it should be in space applications as well. The integrated platforms is really where you get your multifunctional systems that you can use to accomplish your mission objectives, and the combination of 3D structures and 2D electronics can really produce some exciting solutions, whether you're doing it here on Earth or in situ in space manufacturing. So with that, I will stop before Marco gets too menacing and ask for questions. Yes, thank you.